Okay, let's unpack this. We're doing a deep dive today into, well, the heart of network engineering, really, looking at the essential skills, the core concepts, all through a pretty practical lens, interview
Yeah,
questions.
it's a great way to frame it.
Yeah.
Because these aren't just, abstract questions for a test.
Yeah.
They reflect the real-world stuff you need to know to actually build, manage, and, importantly, secure networks. It's about how things actually work day to day.
Exactly. And we've got this resource that lays out questions across key areas, gives us a nice structure.
Yeah.
So we'll cover the basics, routing, security, obviously, design, wireless, keeping an eye on things with management, and even a scripting, automation.
It's a wide field.
It is. So hopefully you'll have some aha moments as we break this down.
Let's jump in.
All right, first up, networking fundamentals. The absolute building blocks. Stuff, as the source says, you just have to know.
Foundational knowledge.
And right away, TCP versus UDP. We hear this all the time. But beyond just reliable and unreliable, what's the real trade-off engineers are making?
It really boils down to reliability versus speed. Simple as that almost.
Okay.
TCP, Transmission Control Protocol, it's meticulous. It makes sure everything gets there in the right order, checks for errors. If a piece is missing, it asks again.
Like registered mail.
Exactly. Whereas UDP, User Datagram Protocol, it's more like, well, just tossing postcards in the general direction, super fast, but no guarantees they'll all arrive or in order.
So TCP is essential for things like loading a web page, email, where every bit counts.
Absolutely. You can't have missing chunks in your email.
And UDP, that's for streaming video, online games, where maybe losing a tiny bit is okay if it means keeping up the speed.
Precisely. A dropped frame in a video call is annoying, but better than a huge delay. Right.
Yep.
That's the trade-off.
Got it. Okay, next fundamental, subnetting. We know it involves dividing networks, but why is this so critical? It feels like more than just organization.
Oh, much more. It's huge for performance. When you subnet, you contain broadcast traffic. It doesn't flood the whole network. And security gets a boost, too. You isolate segments. A problem in one subnet doesn't automatically spill over into others.
Like compartments on a ship?
Kind of, yeah. And, of course, it helps conserve IP addresses, especially important back in the IPv4 days, and just makes managing a growing network way more efficient, scalable.
Makes sense. All right, ARP, Address Resolution Protocol, maps IP to MACH. But what's the actual mechanism? How does my computer find the MP address for another computer on my home Wi-Fi, for instance?
Right. So your computer knows the IP address it wants to reach on the local network, but it needs the physical, the MA address, to actually send the frame.
Okay.
So it basically shouts out an ARP request,
Yeah.
a broadcast message saying, hey, who has IP address 192.168.1.10? Tell me your MAC address.
And the device with that IP?
It hears the shout, sees its IP address, and sends a direct ARP reply back saying, that's me, here's my MA.
And then your computer remembers that mapping for a while.
Exactly, it caches it. So IP gets you to the right network, the right neighborhood, you could say. ARP finds the specific house number, the MAC address, within that neighborhood.
That really clicks. It highlights the difference between MC and IP addresses, too.
Totally fundamental. MEAC, Layer 2, local network, burned into the hardware, doesn't change. IP, Layer 3 for routing between networks, logical, can definitely change.
Okay. Last one for fundamentals, NAT network address translation. Feels super common. How does it work, and why do we rely on it so much?
NAT is basically a translator at the edge of your network, usually on your router or firewall.
Right.
It takes the private IP addresses used inside your local network, the 192.168 or 10.x addresses, and translates them into a single public IP address when traffic goes out to the internet.
So multiple devices share one public IP.
Exactly. That's the main function, especially source NAT. It conserves those precious public IPv4 addresses. It also works in reverse, translating the incoming traffic back to the correct private IP.
My postman analogy wasn't too far off then.
Not at all. And it adds a layer of security, too, because devices on the internet only see your router's public IP. They don't see the internal structure of your network.
Hides the internal setup. Makes sense. Okay, foundations covered. Let's move up a level. How data travels between networks. Routing and switching. Big one here. Static versus dynamic routing. What's the core difference, and when would you pick one path, route, over the other?
Okay, so static routing is manual. You, the administrator, explicitly tell the router to reach network X. Always use this specific path.
Hands-on configuration.
Very hands-on. It's simple, it's predictable, potentially more secure, because there were no routing protocols broadcasting information. Good for small, stable networks or specific use cases.
But the downside?
It doesn't adapt. If that path fails or the network changes, you have to manually update the routes everywhere. Doesn't scale well.
Right, and dynamic.
Dynamic routing uses protocols, think OSPF, EIGRP, BGP. Routers running these protocols talk to each other. They share information about the network topology, learn routes automatically.
So they figure it out themselves.
Pretty much. They use algorithms to calculate the best path based on things like link speed or hop count. If a link goes down, they automatically find an alternative path. Much more scalable, resilient.
But more complex to set up and manage, I imagine.
Definitely. There's more overhead, more potential for complexity and troubleshooting.
The source material specifically mentioned EIGRP. What makes that one special compared to, say, OSPF?
EIGRP. Cisco's baby, mostly. It's often called a hybrid or advanced distance vector protocol. Its killer feature is probably DUL, the diffusing update algorithm.
Okay, DUL.
Yeah, it lets EIGRP calculate backup paths before a primary path fails. So if the main route goes down, it can switch to the backup almost instantly. Very fast convergence.
Faster than OSPF sometime?
Often, yes. And generally considered easier to configure than OSPF, though OSPF is an open standard and may be more common in multi-vendor shops. EIGRP balances speed and relative simplicity, but again, primarily Cisco.
That fast recovery is a big plus. Okay, let's drop down to layer 2. How does a switch actually work? How does it know where to send data inside a local network?
A switch is all about MC addresses. When a frame comes into a switch port, the switch looks at the source MC address. It learns, okay, this MC address lives off this port. It builds a table, a MC address table, mapping MTs to ports.
Like a little address book.
Exactly. Then looks at the destination MC address in the frame. It checks its table and says, that MC is over on port 5. And it forwards the frame only out port 5.
Smart. So it doesn't just blast it everywhere?
Not usually.
Yeah.
Only if it doesn't know the destination MC yet, then it has to flood it out all ports except the one it came in on, hoping the destination device will respond.
Okay. But what if you connect switches with multiple cables for redundancy? That sounds like it could cause problems. Loops?
Big problems.
Yeah.
That's where STP, spanning tree protocol, is absolutely essential.
Right.
If you have redundant paths between switches, without STP, frames could loop forever. Broadcasts become storms, the MEC tables go crazy. The network basically melts down.
So STP prevents that. How?
It intelligently figures out the network topology, identifies redundant links, and then blocks traffic on some of those links to ensure there's only one active path between any 2 points.
It breaks the loop.
It breaks the loop, yeah.
Yeah.
But it keeps those blocked links ready as backups. If the main path fails, STP can unblock a redundant path to restore connectivity, critical for stable switch networks.
Got it. Stability. Okay, last one in this section, link aggregation. Bundling links together, how does that help?
Link aggregation, or LAG, sometimes called ether channel or bonding, it lets you treat multiple physical connections between 2 devices, say 2 switches, as a single logical link.
Okay, some more bandwidth.
That's the obvious benefit, yes. You get the combined bandwidth of all the links in the group. But just as important is redundancy.
Like STP, but for combined links.
Sort of. If one physical cable in the aggregated link fails, traffic just continues flowing over the remaining cables in the bundle. Seamless failover. Plus, it can often load balanced traffic across the links too. Great for performance and reliability.
Makes sense, especially for busy connections. All right, we've got the network built, data's flowing, but is it safe? Let's switch gears to network security.
Crucial topic.
Starting with firewalls. Stateful versus stateless. What's the real difference in how they protect you?
Okay, a stateless firewall is like a basic bouncer with a list. It looks at each packet individually, source IP, destination IP, port, and checks if it matches a rule on its list. Allow or deny. That's it. Doesn't remember anything else.
Simple. Fast, maybe.
Fast, yes, but not very smart. A stateful firewall is much more sophisticated. It tracks the state of connections. Yeah, it knows if a connection was properly initiated from inside your network. So when response traffic comes back from the internet for that connection, the stateful firewall says, I remember this conversation, this packet is expected, and lets it through, even without a specific rule for that incoming packet.
But it blocks unexpected incoming stuff.
Exactly. It understands the context of the traffic flow, making it much harder for unsolicited malicious traffic to get in. Much better security.
Aware of the whole conversation. Got it. What about VPNs, virtual private networks? How do they work their magic?
A VPN essentially creates a secure encrypted tunnel through an untrusted network, usually the public internet.
So like a private pipe through the internet?
Pretty much. All the data going through that tunnel is encrypted, so even if someone could intercept it, they couldn't read it.
And the uses. Remote work is the big one, right?
That's huge, yeah. Secure remote access for employees, connecting branch offices together securely. Also used for privacy, masking your real IP address. Basically, anywhere you need secure communication over an insecure path.
Extending your safe zone. That leads into network segmentation. Why break a network into smaller pieces?
Primarily for security. Containment. If your network is one big flat space and one device gets compromised, the attacker can potentially move laterally and access everything.
Uh-oh.
But if you segment the network using VLANs or subnets with firewall rules between them, you create barriers. A breach in the guest Wi-Fi segment, for example, shouldn't easily allow access to the critical server segment.
Like fire doors in a building.
Excellent analogy. It contains the damage. It also helps performance by limiting broadcast domains, but security is usually the main driver.
Makes sense. Okay, IDS and IPS, intrusion detection and prevention. They sound similar. How do they fit together?
They are related. An IDS, intrusion detection system, is like a silent alarm. It watches network traffic, looks for known attack patterns or suspicious behavior. If it sees something bad, it raises an alert. It
That's you, there's a problem.
Right.
Yeah.
An IPS, intrusion prevention system, does the same detection, but then it takes action. It actively tries to prevent the attack in real time.
How?
It might drop the malicious packets, block the source IP address, terminate the connection. It steps in automatically. So IDS alerts, IPS acts, often deployed together.
Detection and response. Cool. Last security point, ACLs, access control lists. How do you actually manage these? They seem like they could get really complicated.
They can get very complicated, which is why careful management is key. It starts with a clear policy. What traffic should be allowed, what must be blocked, between which segments or devices.
Define the rules first.
Absolutely. Then you translate that policy into specific ACL entries, permit or deny statements based on IPs, protocols, ports.
Yeah.
You have to be precise.
And placement matters.
Hugely. Applying it to the wrong interface or in the wrong direction, inbound versus outbound, can either block legitimate traffic or leave security holes. And you must test them and review them regularly. Outdated or incorrect ACLs are a nightmare. Documentation is vital.
Plan, implement, test, review. Got it.
Yeah.
Okay, let's shift from protecting to planning. Network design and architecture. How do you design a network that can actually grow without falling over? Scalability.
Yet designing for scalability means thinking ahead. You can't just build for today's needs. A key principle is modularity.
Modularity.
Using a hierarchical structure, like the classic three-tier model. You have distinct layers, core, distribution, access, and you can add capacity or new sections within those layers without disrupting the whole thing.
Break it into manageable chunks.
Right. You also need to use scalable technologies. Plan your IP addressing and subnetting with growth in mind. Use VLANs smartly. Build in redundancy from the start, redundant links, redundant devices. And choose hardware that can be upgraded or that supports higher speeds later on.
Future-proofing, kind of?
Exactly. Planning routing and switching efficiently so it doesn't become a bottleneck as you add more users or applications.
You mentioned the three-tier model. Can we quickly recap those layers? Core, distribution, access?
Sure. The access layer is where end-user devices connect PCs, phones, printers, wireless APs. Its job is connecting things to the network.
Got it.
The distribution layer sits above access. It aggregates the connections from multiple access switches. This is often where policies are applied, where routing between VLANs happens, and where you connect to the core.
The middle manager.
Kind of, yeah. And the core layer is the high-speed backbone. Its only job, ideally, is to switch traffic between distribution layers or to the data center or internet edge as fast as possible. No complex policies here, just speed and reliability.
Simple, fast backbone. Okay. And high availability within that design. How do you make sure it stays up?
High availability, or HA, is all about eliminating single points of failure. So redundancy, redundancy, redundancy.
Two of everything.
Pretty much for critical components. 2 core switches, multiple links between layers, redundant power supplies and devices. You use protocols that allow for automatic failover if one switch or link dies. Traffic reroutes instantly through the backup. Things like HSRP or VRRP for router redundancy, spanning tree or link aggregation for link redundancy.
Built-in backups.
Exactly. Plus things like load balancing to spread traffic, preventing overload, and of course good backup and disaster recovery plans for when things really go wrong.
Makes sense. What about data center networks? Any special considerations there?
Oh yeah, data centers are a different beast. Scalability is massive, think thousands of servers. Performance needs are extreme, very high bandwidth, super low latency between servers is critical for modern applications.
So maybe not the three-tier model?
Often not anymore. We see more spine leaf architectures, which are flatter and provide more direct, high-speed paths between any 2 points in the data center. Redundancy is absolutely paramount. Downtime costs a fortune. And security is intense. Lots of segmentation, advanced firewalls, intrusion prevention, strict access control.
High-stakes environment. And nowadays, how do you weave cloud services into the picture, integrating with AWS or Azure, for example?
Integration is key. You need secure, reliable connectivity between your on-prem network and the cloud provider. This usually means setting up secure VPN tunnels or, for better performance and reliability, dedicated private connections like AWS Direct Connect or Azure Express Route.
A dedicated link.
Right. Then you need to think about a hybrid architecture. How do workloads on-prem talk to workloads in the cloud? How do you manage IP addressing across both? Security is crucial, ensuring consistent policies, encrypting data in transit and at rest. And optimizing traffic flow, maybe using cloud load balancers or routing techniques to send users to the closest or best resource, whether it's local or in the cloud. Monitoring that connection is vital too.
Lots to consider there. Okay, let's leave the wires behind mostly and talk wireless networking. The perennial question, 2.4 gigahertz versus 5 gigahertz Wi-Fi. What's the practical difference for users?
There's a classic trade-off, range versus speed and interference. 2.4 gigahertz signals travel further and go through walls better, so you get better coverage area.
But the downside?
It's crowded. Lots of other Wi-Fi networks use it, plus Bluetooth, microwaves, cordless phones. Tons of interference, which slows things down. And there are fewer channels available.
Okay, and 5 gigahertz?
5 gigahertz has way more channels, much less interference typically, so you can get significantly higher speeds, better performance, especially if you have lots of devices or nearby networks. The range is shorter, and those signals don't penetrate obstacles like walls nearly as well, so better speed, less range. You often need more access points for good 5 gigahertz coverage compared to 2.4.
Choose based on your needs and environment. Got it. What about the SSID, the Wi-Fi name? Why is it important besides just picking the right network?
Well, the SSID service set identifier is the public name for the network, how devices find it. Its main job is identification, obviously, but choosing good SSIDs helps organize things, especially if you have multiple networks like guest, corporate, IoT.
And hiding it? Is that good security?
Not really. Hiding the SSID offers very minimal obscurity. It's not true security. Attackers can still find hidden networks easily. Real security comes from strong encryption and authentication like WPA3. The SSID is just the first step in connecting.
Okay, and Wi-Fi channels. What's their role within those 2.4 and 5 gigahertz bands?
Think of the bands like highways, and the channels are the individual lanes. Each channel is a specific slice of frequency. The point is to allow multiple Wi-Fi networks, or access points, to operate near each other without interfering. If two APs are on the same or overlapping channels, they essentially shout over each other, causing poor performance.
So you try to pick different channels.
Exactly. You want to pick non-overlapping channels. In 2.4 gigahertz, there are only really 3 non-overlapping channels, 1, 6, and 11 in North America. That's why it gets so congested. 5 gigahertz offers many more non-overlapping channels, which is a big advantage.
More lanes on the highway. Makes sense. What about mesh networks? They seem popular for home Wi-Fi now. How do they work?
Mesh is different from just using a router and maybe a range extender. In a mesh system, you have multiple nodes, a main router node connected to your internet, and then satellite nodes placed around your house.
Okay.
These nodes talk to each other wirelessly, forming a kind of, well, mesh. They create a single unified network with one SSID. Your devices automatically connect to the strongest node nearby.
And traffic routes between nodes.
Yeah, the system intelligently routes your traffic back to the main router through the best path, hopping between nodes if necessary. It's great for covering larger areas seamlessly, getting rid of dead spots without needing Ethernet cables everywhere.
Clever stuff. And for securing all this wireless traffic WPA3, what's the big deal compared to WPA2?
WPA3 is a significant security upgrade. It uses stronger, more modern encryption methods. One key feature is SAE, simultaneous authentication of equals.
SAE?
Yeah, it replaces the old PSK method used in WPA2 home networks. SAE provides much better protection against offline dictionary attacks, making it harder for someone to crack your Wi-Fi password even if it's not super strong.
That's good.
And it also mandates something called protected management frames, making it harder to spoof or disrupt connections. Plus, it offers better security for open public networks and includes forward secrecy, meaning even if your password gets compromised later, past traffic can't be decrypted. It's just much more robust overall.
Definitely sounds like an important upgrade. Okay, we've designed, built, secured. Now, how do we keep it all running? Network management and monitoring.
Keeping the lights on.
What kind of tools are common here, and what should they absolutely be able to do?
You see a lot of tools like SolarWinds Network Performance Monitor, PRTG Network Monitor, Nagios, Zabbix, lots of options. Open source and commercial.
And the must-have features.
Well, you need basic up-down monitoring our devices online. You need performance monitoring, tracking CPU, memory, bandwidth utilization on links, latency, errors. Traffic analysis is key, understanding what is using the bandwidth, and alerting. You need the system to tell you proactively when something's wrong.
Those alerts seem critical. You mentioned traffic analysis. NetFlow comes up a lot. What does that give you?
NetFlow, or similar protocols like SFlow or IPFAX, gives you visibility into traffic flows. It's not just how much traffic is on a link, but who's talking to who, using what application or port, and for how long.
Like call detail records for network traffic.
That's a great way to put it. It's incredibly useful for troubleshooting. Why is the internet slow? Bob's downloading huge files again. For capacity planning, do we need more bandwidth to this site? And even security. Why is this server suddenly talking to a suspicious IP address?
I see the context. Okay, what's a network baseline? Why bother setting one up?
A baseline is basically a picture of what your network looks like when it's running normally. You collect performance metrics, latency, utilization, error rates, etc. over a period of time under typical conditions.
So you know it's normal.
Exactly. It serves as a reference point. When users complain the network is slow, you can check current metrics against the baseline. Is latency actually higher than normal? Is bandwidth utilization way above the usual peak? It helps you quickly spot anomalies and diagnose problems instead of just guessing.
Makes troubleshooting much more targeted. How do you actually configure those alerts we talked about?
Usually within your monitoring software. You pick a metric you care about, say, interface utilization on your main internet link. Then you define a threshold, maybe 85%. You might add conditions, like if it stays above 85% for more than 10 minutes.
Okay.
Then you configure the action. Send an email to the network team, create a ticket, flash a warning on a dashboard, maybe send an SMS for critical alerts. The tool constantly monitors the metric and triggers the action if the threshold is breached.
Got it. And if you need to dig deeper, how do you analyze traffic patterns? What tools or techniques?
If you need really deep detail on a specific conversation, you might use a packet capture tool like Wireshark. Capture traffic on a specific link and analyze the individual packet.
The ultimate detail.
But that's often too much data. For broader pattern analysis, you'd typically use those NetFlow's flow analyzers we mentioned, or features built into your network management system. You look for trends, spikes, unusual protocols, top talkers, connections to weird places. It helps you identify bottlenecks, misconfigurations, or potential security issues by seeing how traffic is actually flowing.
Okay, looking at all this, monitoring, managing, configuring, seems like a lot of repetitive work sometimes. Which brings us nicely to our last section, scripting and automation.
Increasingly essential skills, for sure.
What languages are typically used for network automation, and why those?
Python is huge right now. It's relatively easy to learn, very readable, and has amazing libraries specifically built for interacting with network devices. Things like NetMiko, Napalm, Scraply. They handle the tricky parts of connecting via SSH, sending commands, and parsing the output.
So Python's the big one.
Definitely the most versatile and popular for cross-vendor automation. But Bash scripting is still very relevant for automating tasks on Linux-based systems, maybe managing tools or running simple device checks. And PowerShell is the equivalent in the Windows world, great for managing Windows servers and also interacting with network gear that supports it.
Right, tool for the job, kind of. How might you use Bash specifically in networking?
Bash is great for stringing together command line tools on a Linux management server. Maybe a script that pings a list of critical devices every 5 minutes and logs the results, or a script to automatically pull config backups from devices using SkiP or Santig, parsing log files with tools like grep and awk to find specific events, automating firewall rule updates on a Linux-based firewall. Simple repetitive tasks.
Makes sense. What about managing configurations across, say, hundreds of switches? That seems like a prime candidate for automation.
Absolutely. That's where tools like Ansible, Puppet Chef, or SaltStack come in. Ansible is particularly popular in networking.
How do they work?
Instead of writing complex scripts to log in and type commands, you define the desired state of your devices in configuration files, like Ansible playbooks, often written in YAML. You say, I want these VLANs configured, this SNMP server set, these ACLs applied. The tool then connects to all your devices and makes the necessary changes to bring them into that desired state.
So it figures out the commands.
Pretty much. It abstracts away a lot of the device-specific command syntax.
Yeah.
Huge benefits. Consistency across devices, speed of deployment, reduced human error, version control for your network configuration. It's a game changer for managing networks at scale.
I can see that. Can you give a quick practical example? A script solving a real problem.
Okay, imagine you need to find out which switch port a specific user's MV address is connected to, but you manage 200 switches. Manually logging into switches and checking AMA tables. Awful.
Yeah, that sounds painful.
A Python script using NetMiko could take the MZ address as input, connect to a list of relevant switches, run the command to show the MAC address table, parse the output to find the port associated with that MEC, and then report back MC address found on switch X, port G10824. Saves a huge amount of time and effort.
Instantly useful. And finally, can you integrate these custom scripts with your main monitoring tools?
Yes, definitely. Many monitoring tools have APIs, application programming interfaces. Your script can use the API to feed custom data into the monitoring system.
Like what?
Maybe your script checks something very specific that the main tool doesn't, like the status of a particular application process on a server or a specific BGP peering state detail. The script gets the data, then pushes it via API to Nagios or PRTG, so it shows up on the dashboard and can be alerted on like any other metric.
Extending the monitor.
Exactly. Or you could have the monitoring tool trigger a script in response to an alert. Like if an interface goes down, automatically run a script that tries to bounce the port or gather detailed diagnostics from the connected device. Automation closing the loop.
Very powerful combination.
Right.
Wow, okay. We've really gone from the basic OSI layers right up to automated network management. A huge sweep.
It covers a lot of ground, yeah. And seeing it through the lens of these interview-style questions really highlights the practical knowledge needed. It's not just theory. It's about applying these concepts.
We hit protocols, security best practices, designing for growth, wrangling wireless, keeping tabs on performance, and the increasing need for scripting.
It paints a picture of a modern network engineer.
And, you know, the source material mentioned something interesting about evaluating engineers, suggesting that skills tests, actual practical tests, might be better than just interviews alone.
That makes sense. Demonstrating you can do it, not just talk about it.
Which leads to a final thought. With technology changing so fast, especially with automation taking over some traditional tasks, is how we learn and prove our skills changing too? Are we shifting more towards needing to show demonstrable, hands-on ability, maybe through labs or projects, rather than just certifications or interview answers? What does it mean to be a skilled network engineer in this rapidly evolving landscape? Something for you to ponder.